Okay, we're continuing on with section 2.2. I want to go ahead and look at an example for quantitative data where we've done the grouping with single values and see how that's different from when we have classes. So let's look at this example. The frequency and relative frequency distribution for the homework scores for 44 students are given below, and we have scores from 0 to 5. They've given us frequencies and the relative frequencies. And they want us to construct a relative frequency histogram for the data, so we're going to be using these relative frequencies over here for the height. So let's go ahead and start out by drawing in our axes and figuring out what our scale will be. So I'll draw in the vertical on the far left and the horizontal on the very bottom. And just while I'm getting this lined up, it's worth mentioning that for whatever reason, a lot of times students forget to draw in the axes and they just kind of assume the bottom line is their horizontal and the far left is their vertical, but those do not need to be drawn in. And then so on our horizontal, that's going to be the score. And on the vertical, that one's going to be our relative frequency. And then we want to think about what would be a good scale or numbering to put on that. So let's go ahead and do the relative frequency first. The trick there for me would be to always look at the largest relative frequency, which in this case is this 0.3636, and think about trying to make sure that goes more than halfway up the vertical and that I've chosen a nice numbering scale for that. So what I want to do is count the squares. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 squares to work with, and I need to make it up to 0.3636. So what I do on the calculator is I take that maximum relative frequency of 0.3636 and I divide that up among 8 squares. And then if I take this and used it as my scale, that would get me from 0 up to 3636 at the top. But this is a messy scale, so I want to round that up, but just a little bit, to something nice, and 0.05 would be a little bigger and a nice scale, so I'm going to go with 0.05 for my scale on each notch. The scale is a reference to what each square is. I often don't like to number each square, so I am going to use a scale of 0.05, but you'll see what looks like a numbering of 0.10s because I'm numbering every other one. But really it is a scale of 0.5 because scale is about each square, so 5, 10, 15, 20, 25, 30, 35, 40. And then on the horizontal, I want to leave a little bit of room to make a break in the scale, so I'm going to go ahead and put my 0 right here. And I have, if you count across here, you actually have 15 squares, and I have 6 of these to get drawn in. So I'm going to do every other one to spread these out a little bit. And then there's just one tricky piece to this that I want to kind of alert you to and show you how we're going to deal with. So I'm going to draw one of these in. At first I'm going to draw it with a pencil because it's not going to be correct at first, so you might want to just watch at this point, wait till I switch back to pen. But let's say that I drew a bar right here, and I'm not actually looking at any of the numbers right now, so I'm not trying to get that height right for any of these. But if you were to look at that and think about which bar is that the bar for 2 or is that the bar for 3? I think it's reasonable that some people could get mixed up and that some people might think it was 2 and others might think it was 3. From our rule that we had up above, we know that we're supposed to go from lower cut point of the class we're on to the lower cut point of the next class. So this is supposed to be the lower cut point of the class we're on, and this would be the next one. So this should be the bar for 2. But again, not everybody that's going to see our graphs is going to know that rule. So I think that what we want to do is design a system that makes it very clear what that one's for. And so the way we do that is we put the bar directly over the number that we want it to represent. So let me go ahead and erase this one that I did in pencil, and then I'll bring in the pen and show you what I really would do for the bar for 2. So when I go to graph that bar for 2, I would see, let's see, 0.682 is its relative frequency. So what I'm going to do on that one is I'm going to start right in between the 1 and the 2 for the left side of the bar, and right in between the 2 and the 3 for the right hand side of the bar, and I'm going to draw that to the height of 0.068 and just do the best I can with 0.68, which is kind of a messy number, but this is 0.5, that's 10, so that seems about right. But if you notice what I'm doing, I'm making that bar go from 1.5 to 2.5 so that that bar is sitting right over the top of the number 2, and by doing that it should take out any confusion about is that the bar for 2 or is that the bar for 3. So if we did that the whole way through, then on the bar for 0 we'd want that same height that we did for that one, and we'd start a half to the left and a half to the right on that one as well, and that would be the same height as the last bar. So there's the bar for 0. And then the bar for 1 is a little shorter, 0.455, so that'd be just below the line for 0.05. The shading is optional, but usually a good idea to help distinguish the bars. And then the bar for 3 goes up to just over 20. The bar for 4 is our tall one at 3.636, so just a little above the 3.5 line. And then the bar for 5 goes up to 0.25, so that's right on one of our notches right there. And then I'm just going to go ahead and shade in the rest of those to finish it off. I do like to use different shading on bars that are next to each other, so I'm just using different direction diagonals so that they're a little bit distinguished visually. In addition to their height, we can see the slightly different pattern. Alright, so that's our relative frequency histogram for single value grouping. And the main thing that we want to notice that was different there is that the bars did go from half mark to half mark rather than lower cut point to lower cut point. And again, that's just to emphasize that this is the bar for 3, not 4. And doing that half mark to half mark takes out all that confusion. So that's something we only do for single value. If it was classes of data, we would still go from lower cut point to lower cut point like before. But note, the bars do start and end at the half marks for single value grouping. Okay, so we're continuing on with section 2.2. We finished doing the graphical displays for quantitative data, and we're going to now move on to the graphical displays for categorical data. We're going to return to the network data that we looked at in the previous section, where the networks are ABC, CBS, and NBC, and we had done the frequency and relative frequencies previously. And now we're going to do two things for that. One of them is we're going to construct a pie chart for the relative frequencies. So a pie chart, as you're familiar with, would be based on a circle. So I'm just going to do the best I can to freehand a circle here. Don't worry about it being perfect. And then I'm going to just draw in the wedges by hand as well. And we're going to do this for the relative frequencies. So we're considering the percentages, 25%, 40%, and 35%. And when you go to do those, you want to pick one that would be easy to do first. So I would probably go with the 25% from ABC first, since that's 1/4 of the circle. So I would draw that in. I would label that as ABC, and then I would put the 25% in there. Even though it does say to do it for the relative frequencies, it's more common on pie charts to label them as percentages than in decimal form. And then when it comes to do the 40% and the 35%, I'm just going to do the best I can with those. I'm going to kind of imagine splitting this remaining part in half. And then I'm just going to miss that a little bit on purpose. So it looks like, to me, this one's a little bit bigger. So this one I'm going to call CBS and 40%. And then this wedge over here would be the remaining 35% for NBC. And that's the way we would go about doing a pie chart by hand. Technically, we should be doing things like drawing the circle with a compass and measuring our angles with a protractor to make sure we get the right percentages of the circle. But really, if we want that level of detail, we would just be doing this on technology, maybe making a 3D pie chart with our network's wedge slid out from the rest of the pie to emphasize it. And then just other things to note: if you ever have a pie wedge that's too small to do the labeling, it's okay to draw a line off to the side and do the labeling outside of the circle. Okay, so that's part A with the pie chart. On part B, they want us to construct a pie chart for the frequency data, and that's actually already done here using technology, but I do want to point out a few things. They asked for a frequency pie chart, so I did label just 0, 1, 2, 3, 4, 5, 6, 7, 8. Choosing 8 as the max because that was the biggest frequency we had in our chart anywhere. And then you might notice on the horizontal that instead of having a number line, I've just labeled each bar. So this is the bar for ABC, CBS, and NBC. I just did them alphabetically, like they were in our table. Sometimes people will choose to do them tallest bar to smallest or smallest to largest. There's no specific order required on a bar chart. The other thing that you will notice that's different than the quantitative data is for categorical, since there's no logical flow from ABC to CBS. You don't just, like, if you get too big for ABC, you're not all of a sudden in CBS automatically. Since that natural flow is not there, we have these gaps between the bars that we did not have when it was quantitative. So we'll make a note of that before we move on. So since there's no natural flow from one class to another, there are gaps between the bars. And again, that note applies to categorical data only. We're not supposed to have gaps like that if it were quantitative data. All right, now we're going to go ahead and move back to the quantitative data for a little bit and look at something called a dot plot. A dot plot is a simple graph that's used to show the location of all the data values. And dot plots can be useful for showing the relative position of the data, and they make it easier to spot gaps and clusters in the data set. So let's consider this data set down here, looking at this example. Construct a dot plot for the following exam scores of the students in an introductory statistics class. So here we have some exam scores, and the dot plot has actually already been made, so again I'll just mention some details on that. For a dot plot, we only do a horizontal number line, there's no vertical number line. And then just make sure you have a consistent scale. So I did this on technology, and the default there was a scale of 6, which is actually a little bit awkward. If I was doing this myself by hand, I probably would have chosen a scale of 5 and went 30, 35, 40, 45, 50. But we'll deal with the 6 that they gave us. That's fine. And then as far as making the dot plot goes, you would just take the number 88. You'd go to your number line, you'd find 88, and you would plot a dot right there. So it's basically just like it sounds, and you just continue on that way. So you get to 76, and you'd go over and you'd plot that dot, and 63, and you plot that dot, and so on. So you would do that for the entire data set. And a couple things that are worth noting is it looks like we have a stack here and a stack there. And the reason we have a stack here is because the number 89 shows up once here and again there. So when you have two values that are repeated, we just stack them on top of each other. And so the same thing happened with the 96. So we can look for those. We have a 96 right here, and there must be a 96 somewhere else. There it is. So when you have those repeated values, you just stack them. And in fact, even if the values were just so close to each other that they were going to touch, you would still stack them. When I'm making one of these, I don't double check to make sure it's an identical value before I stack. If I go to put a dot on the number line and there's already a dot in the spot where I'm headed, then I will just stack them. So let's fill in a note on that. If two or more data values will lie in the same place or extremely close to each other, then just stack them. And that would be our dot plot. And then the dot plot's use comes in showing gaps and clusters. So one of the things I notice when I look at this graph, especially these two values over here stand out to me. I would refer to those as outliers probably because they're so far away from the rest of the data set. And then I might notice like a gap here and a gap there and maybe a gap here. So I might think about those as letter grades A, B, C, and this section would be the D's, but maybe there aren't any, and then these would be the F's over here. So sometimes once you get this data displayed on the dot plot, it's a little easier to see where those breaks in the data are, and then also to see data values that stand off on their own, which again, we refer to those as outliers, though we'll officially define that later on in Chapter 3. Okay, so the last topic for this section is misleading graphs. We've been doing all these graphs in this section. We've done the pie charts and the bar charts and the histograms and the dot plots. And one of the things we want to avoid is misleading graphs. So let's look at a definition and an example with that. So when we make graphs, we want to make sure that we make them in such a way that they do not mislead the reader. We also want to make sure we don't let other people mislead us with their graphs. So if you're being a consumer of statistics and people are presenting graphs to you to try and persuade you, if they are doing something misleading, you want to be able to notice that. So consider the graph below for the medal count for the top 10 countries at the 2010 Winter Olympics. So we've got the medal counts for USA, Germany, Canada, Norway, Austria, Russia, South Korea, China, Sweden, and France. And they've just been arranged in descending order, so we've gone from the most medals down to the least in the top 10 anyways. And then let's look at the questions that we have here. So if you were to just look at the bars but not the scale, then how does the number of medals for South Korea compare to the number for China? So we've got South Korea right here and we've got China there. And if I just compared the heights of those bars, I might say that the bar for South Korea is about 4 times as tall for the one for China. So I might say that there is a 4-to-1 ratio for South Korea to China. But if I were to look at the scale, then what's the actual ratio for those countries? So now when I start trying to look at the scale, I'm trying to go from South Korea and look across and say, all right, so how tall is that? And it looks like that it might actually be the case that they won 14 medals. And if I went across for China and did the same thing, it looks like that might be right around here, so maybe that's around 11. So when I look at the scale, it seems more like a 14 to 11 ratio for South Korea to China. So if we just looked at it visually like we did in Part A, then I would say that this is pretty misleading because it looks like there were 4 times as many medals for South Korea as there was for China. But when you look at that based on the scale, it looks like there was actually 14 to 11, which is nowhere near 4 times as many medals. So if China has 11 and South Korea really had 4 times as many, they would need to have 44, not 14. So why is it that we got so confused on the visual? Why did it look like 4 times as many medals for South Korea? And that's the question they're asking us in Part C. What mistake was made in creating this graph that makes it misleading? And basically what's going wrong here is the scale. So if you look at the way this is numbered, it goes 10, 15, 20, 25, 30. So that's a consistent scale in the sense that it keeps going up by 5s. But what's wrong with it is it doesn't start at 0. They started their scale at 10. So we refer to that as truncating. So I would say this is a truncated scale. And so what I'm saying there is the problem is they started at 10 rather than 0. And that would be the vertical axis I'm referring to. And anytime you do this, where you start your numbering somewhere other than 0, you run the risk of creating a misleading graph. And another way that graphs can be made misleading is if the scale is not consistent. So we do have a consistent scale on this one. It does go 10, 15, 20, 25, 30, 35, 40. Sometimes people will go 10, 15, 20, and then they switch their numbering, and then they do like 30, 40, 50. So they go for 5s for a while, and then they switch to 10s. And that will also create a very similar distortion in the height comparisons of the bars. So we always, if we're drawing bar histograms or bar charts, then when these bars are dropping all the way down, they need to drop all the way down to 0, and we need to have a consistent scale here. So let's make a note about that. So to avoid misleading graphs, we need to make sure that we have a consistent scale for any part of our axis that spans part of the graph we are drawing. So we need a consistent scale. And then for graphs that extend all the way down to touch the axis, make sure that you begin your numbering at 0. So it's those two things you're looking for, starting your numbering at 0 and then having a consistent scale. So a couple other notes about this while we're looking at it. One of the questions that I often get from students in class is, would it be okay to make like a double slash mark right here? Would that fix the problem? And the answer there is no, because if you make a double slash mark on your vertical scale, we consider that slash mark to be going all the way across. And so if you're cutting the scale here, then you're cutting out part of the bars. Sometimes people even make the graphs and they will show a break like that in the bar. They usually do it as a gap. And in some ways that's kind of helping. It's like admitting to the problem, but it doesn't fix the problem. You can make those little slashes, but the ratios still look wrong, and there's no way for the reader to figure out what the right ratio is other than to look at the scale. And if what we really wanted them to do was to focus on the numbers and look at the scale, then we would have presented this just in a normal chart and they could look at those numbers. But when you make a bar graph, you're telling them, here's a visual interpretation of this, but when you make that cut here, which goes through your bars, then you are distorting that visual, and it makes your graph essentially worthless. All right, that's it for this section.